This video is on springs in parallel. Let's talk a little bit about springs in general first. Here we have just a single spring with a mass hanging from it. Here we have two springs. These are in series. Each has an equal spring constant. We have the same mass here. And then we've taken those springs and we've oriented them in what is called parallel. Your previous experience might be enough to help you answer these questions. Which of these systems is the tightest? That's going to be when the springs are in parallel. Which one is the flopsiest? When the springs are in series. Which will take the most time? That's when the springs are flopsiest. And which will take the least time? That's when the springs are tightest. So it turns out if you add a second spring into a system, it depends on how you add it as to what effect it's going to have. If you add it in series, the system is going to become flopsier. If you add it in parallel, the system is going to become tighter. And so we are going to deal here with springs in parallel. You can see the picture there. Those springs are in parallel. Each of them has a certain spring constant. There's a certain force, therefore, in each spring. There's a certain amount of displacement of each spring whenever we pull with an applied force over here on this side. What we want is we want the effective spring constant for this system. Now, which of these two choices will be true when we apply the force here? Well, when we apply this force, isn't it true that the total displacement that I've labeled here will be numerically equal to these displacements? So I think 0.4 is going to be true. And what else will be true? This total force that is applied has been divvied up between F1 and F2. So F1 and F2 together would give us the applied force. So that's going to be important. I've recopied the answers that we got from the previous page right here. One part C answer should have a plus symbol in it. There it is right there. Use Hooke's law to transform that answer's equation from the one type of variable that it already has into the other two types of variables that are in Hooke's law. Well, Hooke's law, as you recall, shall I write it over here, is that the force in a spring is equal to, numerically, the spring constant times the stretch. I'll leave the negative sign off for now. Well, we have force in this equation, so what we're going to do here is F1 would be K1 times X1, and F2 would be the spring constant of spring 2 multiplied by its displacement, and the applied force would have the effective spring constant multiplied by the total displacement. We've just taken this equation right here, we've used Hooke's law with it to get that. The other part C answer should have all equal signs. X1 and X2 and X total are all the same. I can just call those X if I want. So I'm going to rewrite this equation as K1 times X plus K2 times X, because it's the same X, equals K effective times X. And then what? It's all X's. I can divide through by that, and that means that the effective spring constant, whenever we have springs in parallel, is just the sum of those. If we had three springs in parallel, then the effective spring constant would just be the sum of all three. You just use the add 'em up rule for springs in parallel when you're trying to find the effective spring constant.